Hello, and thanks for joining us. On behalf of the Environmental Finance Center Network, I'd like to welcome you to today's webinar, Risk and Resilience, Assessing Vulnerability for Coastal Communities. My name is Tess Clark. I work here at the Syracuse University Environmental Finance Center. I'm happy to report that we have about 150 registrants today. You can see that people are joining us from all over the world. And you can receive a certificate of attendance for viewing this webinar today from the American Waterworks Association. This webinar has not been submitted to licensing agencies for pre-approval of continuing education credits. You must check with your licensing agency to learn about its criteria, rules, and what you need to do in order to receive credit. For attendees who have an AWWA customer record, your certificate will be uploaded within 30 days. For attendees that do not have a customer record, you will receive an email from AWWA requesting that you create a customer record by a specific date to receive the certificate. If you don't do this, unfortunately, you will not receive a certificate. All right, so on that note, I'd love to hand over the presentation today first to our presenter from the University of Maryland, Brandy Espinola. Brandy is Program Manager at the University of Maryland Environmental Finance Center. All right, Brandy, take it away.
Hi, Tess, and thank you. Thank you all for joining us. Today, I'm really just here to introduce our expert resilience program manager. And so you'll hear over the next hour from Danielle Swallow. She's a coastal hazardous specialist with Delaware Sea Grant, where she provides technical assistance and outreach on community resiliency to storms, sea level rise, and other hazards. She is a co-founder of the Resilient and Sustainable Communities League, RASCL. RASCL is a professional network of organizations dedicated to helping communities thrive in the face of changing climates and environmental conditions. And previously, Danielle managed the Resilient Community Partnership Program at DENREC, Delaware's Coastal Program Office, and helped develop the state's new sea level rise planning scenarios. Prior to that, she spent over 15 years at the National Oceanic and Atmospheric Administration in Washington, D.C., where she specialized in climate policy and marine operations. So Danielle really is an expert in resilience, and we thought that she'd be able to come and bring a great perspective on specifically coastal issues for resilience. She'll be the first to tell you that she's not a small water systems expert or an operator, but as we were discussing earlier today, the resilience planning and assessment tools and principles really can be applied to any utility or any community, any system. And so we are grateful to have her here speaking on behalf of resilience, specifically coastal community issues. And so I'm just going to hand it over to Danielle. And at the end of the session, we'll go ahead and have a facilitated Q&A. So please feel free to type in your questions throughout the webinar, and I'll go ahead and facilitate that at the end. Thank you.
Hi, everyone. Thank you very much, Brandy. As Brandy mentioned, I'm Danielle Swallow. I'm a coastal resources hazard specialist with Delaware Sea Grant, and I'm very happy to be here today to talk with you and walk through some concepts for risk and resilience and applications at the community level so that we can make our communities better prepared for the changes that are coming and currently they're experiencing related to climate change and extreme events. And as Brandy mentioned, I kind of work across different types of infrastructure and community planning. I'm not a small water operator, but I did try to pepper my talk today with examples that relate to that area. And but I do want to caveat that I'm going to focus a lot today on a specific type of hazard planning, and that's related to flooding from sea level rise and storms, heavy precipitation events, and that kind of thing. Okay, so just a quick word about Delaware Sea Grant. We are a NOAA-funded program that is based at the University of Delaware. A Sea Grant program, it's a national network, and it functions like a land grant. Basically, we provide extension services, research, and education and outreach to communities. And we are basically working to connect science with decision support at the community level. We're trying to translate research and science and help communities apply it to improve decision-making capabilities at their local level. And I'm essentially an extension agent working directly with all kinds of stakeholders, but I do spend a lot of time at the municipal and community level, working with them to provide training, technical assistance, and capacity building to help them navigate these questions about resilience. And I'll talk some about that now. But first, I wanted to give you an overview of today's presentation. It's divided into 5 parts. Part 1, I'll cover some basic risk and hazard concepts. Part 2, I'll kind of walk through some climate projections and implications for water systems. And by no means is that going to be an exhaustive exploration of climate projections, but I'm touching on some of the key findings at the global and regional scale here in the Mid-Atlantic. And in part 3, I will talk about building resilience through assessment and planning, and sort of what are some basic steps for resilience planning. And then I'll cover in part 4 a couple of examples, as time allows, that relate to small water systems or community planning that includes thinking about water infrastructure. And then I'll leave off with some additional resources to investigate on your own time. So let's get started with risk and hazard concepts. And first, we start with hazards. Since today's focus is going to be on flooding, I wanted to just characterize types of flooding or causes of flooding. As we know, a hazard is a natural phenomenon that can produce harm or have undesirable consequences. And here in Delaware, our most prevalent hazard is flooding. And it can arise from the following 4 sources that I've listed here. We have heavy precipitation events, which are those rainstorms that aren't necessarily tropical or subtropical in nature, but they dump quite a lot of rain in a short amount of time. We have coastal storms, which I kind of put in the category of those tropical systems or nor'easters that can also bring a lot of storm surge and erosion forces, wind damage with them. And we have, I'm going to skip over the next one for a second and go to tidal flooding. We are a very low-lying state. We actually have the lowest mean elevation in the United States, and we're very flat also in our terrain. So typically on a given day in many parts of Delaware in low-lying spots, there could be some periodic flooding at high tide in driveways or parts of roadways. We can call that nuisance flooding. And then there's sea level rise, which I'm going to spend a fair amount of time on today discussing. Sea level rise kind of amplifies the risk of flooding from all these sources, and so it's an important consideration for flood risk. So when thinking about hazards and risk, it's important to investigate exposure. Exposure is an indicator of the people, property, systems that are within the area that could be affected by a hazard. They're basically in the path of that hazard. So here in Delaware, we're experiencing a lot of population growth along our coast, particularly in the southern part of the state, where we have fabulous beaches and resort towns. And that's bringing with it a lot of development pressure. So we are doing quite a lot of building in the floodplain. And that means we're putting more people, more property and infrastructure in the path of exposure. But just because a person, place, or thing is exposed to a hazard, it does not necessarily mean that there will be an effect. That is a function of vulnerability to that hazard. So vulnerability implies someone or something being more susceptible to impacts if exposed to a hazard. And there are many things that amplify or can lessen vulnerability. And I've listed just a couple of examples here. Building codes and land use decisions can influence vulnerability. For instance, if we're building homes in high-risk flood zones, building in the floodplain is generally a risky practice, and especially if you don't mitigate it with strong building codes, that influences the design and the ability of the home to withstand a flood or other hazard. But on the flip side, if you are building homes in the floodplain and buildings and you're elevating them and you're building to higher standards, such that you might have living space that is well above the base flood elevation, or you have your utilities elevated, or you're taking on and doing some dry proofing and wet proofing measures, then you may reduce that vulnerability to flooding. But realize that the road, the driveway to the house, maybe the car parked in the driveway, those are still in the floodplain. Those are still exposed, and they're hence more vulnerable. I list at-risk populations because studies show that at-risk populations, such as older adults or low-income individuals, can be disproportionately impacted by flooding. And research shows that this population can be slower to recover from the disruptions caused by severe weather and emergencies. Again, here in Delaware, we actually have, in the county that I reside in, Sussex County, by 2030, we expect over 30% of our residents to be over the age of 65, and that's compared to 23% statewide. And the number of 85-year-olds and up in my county will increase dramatically, nearly a threefold increase from 2010 numbers. So that's really because this community, this area is drawing a lot of retirees. And where are they moving? They're moving to the coast and into the floodplain. I also list nature-based systems because during flood events, nature-based systems such as riparian buffers and wetlands can slow runoff and absorb excess water. So this can reduce peak flows, it can lessen downstream flooding, so it actually can reduce vulnerability for neighborhoods, towns, and utilities. So there are all kinds of ways that vulnerability can increase or decrease depending on what you're looking at. And when thinking about vulnerability, it helps to look at both sensitivity and adaptive capacity. Sensitivity means how susceptible something is to damage or harm, or maybe economic loss from the exposure. An example might be a house with a basement in the flood zone. That could potentially be more sensitive than a house without a basement. Or a power generator that is at or below the base elevation for flooding, that potentially is going to be more sensitive to flooding than one that wasn't. And adaptive capacity, that means that's basically looking at whether the asset or facility can adjust, can repair, or adapt to the event. An example might be wetlands, that if they have room to migrate as sea level rises, then it's been proven that they can adapt and manage the change. But in terms of built infrastructure, sometimes the question is, can it be elevated, flood-proofed, or secured? If so, it'll have more adaptive capacity than those facilities and structures that cannot. So an example is a chemical or propane tank. If you have it in your utility, can it be secured or elevated to prevent it from floating away in a flood? That's a question of adaptive capacity. An example of something with less adaptive capacity might be a low-lying overflow pipe that's aging. Maybe those pipes are not in good condition. They could be leaking. And even if you put a backflow preventer in to sort of protect the finished water, there is risk that those pipes may not function properly and manage the flooding event. So that could be an adaptive capacity issue. I think a key point here to share with you is that stressed systems are more likely to be sensitive or have reduced adaptive capacity. So a water storage tank with a little extra capacity for those emergencies when you're going to want to top off the water storage, so you have that water in case of power going out or other deterioration of the system due to a flooding event. If you don't have the capacity to begin with, then that system basically is not going to have a lot of adaptive capacity. Another example are drains and culverts that might be clogged. Those are systems that are stressed already, so if you have a flooding event, there's less capacity there for them to handle that flooding. Another stressor are development patterns that can leave little room to relocate facilities or infrastructure decay due to age and poor maintenance. So when you look at this table, basically, to give you an example, if a water tank is highly sensitive to exposure from floods, but it has low adaptive capacity, it's highly vulnerable. But if an office has relatively low or even medium sensitivity and high adaptive capacity, because maybe you could easily relocate that office to higher ground, then it's going to have lower overall vulnerability. And so the nexus of hazards, exposure, and vulnerability is risk. And a low risk might be an infrequent hazard that even if it occurred, it had limited assets exposed or damaged. And a high risk would be a hazard that occurs somewhat frequently and or for which there maybe were exposed and vulnerable assets. And it's important for every community, every utility or business to assess and identify its risks and also what its tolerance for risk, because we all live with risk to some degree. So understanding your tolerance for how much risk you're willing to accept, maybe how frequent a disruption you're willing to accept, or how long a disruption you're willing to accept, particularly in terms of how long it takes you to recover. Those are important questions for you to think about. We have control over vulnerability and exposure. We have less control over our hazards, but that can vary, of course, depending on the hazard. But in general, we're going to have more control over vulnerability and exposure. And so this brings us to the important concept of resilience. Resilience is the capacity to bounce back quickly from hazardous events or other disruptions. And obviously today I'm focusing on natural hazards and climate hazards. But you know, there's disruptions of all kinds. There's economic downturn. There's technological issues. There's other man-made, you know, terrorism acts and all kinds of disruptions that go on. But you know, we're going to focus the rest of this discussion on the natural and climate-made hazards. But these same principles apply across the board. And of course, you know, in the headlines with the emergencies we've had with Hurricane Matthew and Florence, you can certainly see that that communities are impacted differently by hazards, and some fare better than others. Some take longer to recover than others, and that has a lot to do with resilience planning. Resilience planning is anticipatory. It's about assessing the risks of exposure to future events like floods, and then being proactive to take the steps now to reduce vulnerabilities. When we're proactive and we take measures to minimize disruptions, it helps us recover more quickly. And that saves us time and money in the long run, as well as protects public safety. And FEMA reports that for every dollar spent on mitigation, we save $6 in future avoided losses. That's a key metric. I put up this graphic here regarding resilience in the built environment because I find it helpful because it gets back to that issue of stresses, a stress system, and how quickly it can function. In terms of the built environment, like water systems, resilience can be characterized as regaining functionality as quickly as possible after an event. Functionality is a measure of how well a building or infrastructure system operates and delivers its service or meets its intended purpose. And the time to recovery of function is how long it takes before the system is adequately functioning again. So the more you plan now to anticipate risks and address them, the better off you will be. And that's where resilience planning comes in. And so what this graph is showing essentially are two examples of systems. A is a system that has had improvements made to it and has been maintained over time. And B is a system that's aging. So you can imagine it hasn't had the same upgrades or improvements made to it. Both are subjected to a hazardous event. You'll see an immediate drop-off in functionality, and then the recovery time is shown there on that graph. It's the time that elapses before the critical functionality is regained. And you can see that the system that has had improvements to start with has regained some of its core functionality sooner. And so that's important in terms of resilience, because we want to get back to that need to bounce back more quickly, so we can provide the services that we need to society and maintain continuity of operations or quality of life for our citizens. By the way, this is from a NIST guide, which I have a link to at the very back of the presentation. So now we're going to go to part 2, future climate projections. And again, I'm going to kind of run through this a bit quickly. I'm not going to cover it in an exhaustive sort of way, but to give you kind of a sample of some of the projections that are there and that can impact us. And when I'm referring to these projections, today I'm using information from the Intergovernmental Panel on Climate Change. This is a group of global scientists who have reached consensus and provide a lot of the global projections from which our federal and state agencies base their individualized projections. I include temperatures, although most of my talk will be about more of the wet kinds of things, but I wanted to have an example on here regarding temperatures. This graph shows that is showing extreme temperatures over the last several decades. It's kind of giving you a near history of what's been going on. The red bars indicate a year with more daily record highs than daily record lows, while the blue bars indicate a year with more record lows than highs. And the height of the bar indicates the ratio of record highs to lows, that's the red, or of record lows to highs, which is blue. According to the consensus of scientists in the world, both extremely cold days and extremely warm days are expected to become warmer in the future. Cold waves are predicted to become less intense, while heat waves will become more intense. And the number of days below freezing is projected to decline, while the number of days above 90 degrees will rise. So I could imagine that the decrease in extreme cold temperatures could mean, potentially fewer water main breaks, if I'm thinking about examples for water infrastructure. But excessively hot weather could also cause those same pipes and mains for the ground soil to shift underneath and the ground to swell, and that could also stress those same water mains. Regarding precipitation intensity, heavy precipitation events in most parts of the United States have increased in both intensity and frequency since 1901. But there are important regional differences, with the largest increases occurring in the northeastern United States. And you can see this chart. It shows the amount of precipitation falling in daily events that exceed the 99th percentile of all non-zero precipitation days. Whew, that's a mouthful. What they're saying is that it's basically representing the top 1% of all daily precipitation events. And further, the scientific community is projecting that the frequency and intensity of heavy precipitation events will continue to increase over the 21st century. Regionally, though, the northern United States, including Alaska, is projected to receive more precipitation in the winter and spring, and parts of the southwestern United States are projected to receive less precipitation in the winter and spring. But imagine heavy precipitation. It can overwhelm stormwater management systems if there is not sufficient capacity, or if those systems are stressed. The ground becomes saturated. It's unable to absorb and slow runoff, and so you could have an increased risk of floods. So that's just an example, but basically the finding that there's going to be more precipitation intensity is a really important finding that anyone who's looking at infrastructure, particularly anything dealing with water supply, water quality, that needs to be looked at, as well as even our transportation systems and other infrastructure. So here on the East Coast, we take notice of hurricanes quite a lot, and the scientific community projects an increase in the intensity of hurricanes in the North Atlantic. And that could increase the probability of extreme flooding along most of the U.S., Atlantic, and Gulf Coast states beyond what would be projected based solely on relative sea level rise. The science community I think there's still some dispute as to whether climate change is creating hurricanes. I don't think that that's necessarily where they're settling. They're feeling that climate change is having an influence over the warming of the oceans, which is feeding water vapor into the atmosphere, and that's feeding the intensity of the storms. So there's still some low confidence related to whether climate change will increase the frequency of hurricanes, but there's more and more coalescing around the fact that the intensity of hurricanes will increase. And certainly some of the recent hurricanes we've had this year and last year with Hurricane Matthew and Florence and Harvey in Texas last year, and the tremendous amount of rain that was dumped on Texas, I think that gives us kind of an early warning sign about the impacts of hurricane intensity on communities. And now sea level rise. Sea level rise, as we know, the volume of water is expanding due to warmer temperatures and ice melt, and sea level rise appears as an increase in the average high tide over time. Relative to the year 2000, global mean sea level is very likely to rise by 0.3 to 0.6 feet by 2030, 0.5 to 1.2 feet by 2050, and 1 foot to 4.3 feet by 2100. And there's the projections are based on different emissions pathways that have to do with how much greenhouse gases is going in the atmosphere and how our globe responds to it. But there's pretty high confidence that no matter how much or how little mitigation of greenhouse gases will go into the future, it's going to have little effect on the projected global mean sea level rise in the first half of the century. Where it can differ is in the second half, depending on how much mitigation is done. Here in Delaware, we actually developed our own set of sea level rise scenarios that are based on the global models, as well as some regional differences. Because here in the Mid-Atlantic, and here in Delaware in particular, our local mean sea level is rising at twice the global average. We're in a hot spot for sea level rise. In Delaware, that has to do with land subsidence that we're experiencing and other factors, including a weakening of the Gulf Stream off of our part of the coast, which is stacking more water up toward our local coastal waterways here. In Delaware, we're projecting 1 to 2 feet of sea level rise by 2050. And these are a set of projections that Delaware came out with at the end of 2017. Again, working from the global models and also regionalizing it to, based on some of the characteristics I've just described that add to our vulnerability and exposure. So here in Delaware, we came up with these projections as a planning tool, and there's projections at the national level through the IPCC, this global consensus group, as well as at the federal level. The Army Corps of Engineers produces projections, NOAA has projections, and others. And so it's important to consult with projections to kind of understand how much risk you might be experiencing into the future, and recognize that these projections are planning tools. They're not predictions, particularly because as you go further out in time, global emissions mitigation can change and influence the rate that we experience an increase in sea level rise. But there's a lot of confidence in how things are going, and so these projections become a planning tool for us. In Delaware, what this chart does is it gives us an opportunity to select the time frame we want to plan to, as well as how much risk we want to take on. The high curve is the red curve. That shows that there is 95% confidence that sea level rise will not exceed any of the thresholds along that part of along the red curve for any given year. The intermediate curve is the green, 50%, and the low is the 5%. That means there's 5% confidence that sea level rise will not exceed any point along that curve. And so if we're thinking about infrastructure that has a particular public safety importance to it, maybe that has to do with a wastewater treatment plant or a fire station, and we're planning 30 years out, or 50, maybe 30 years out, let's say, thinking about where to locate the fire station or plant, we're going to potentially select the red high bar, which is the 95% curve, because we have a low risk tolerance. We don't want to get our projections wrong. We want to be able to plan for as much risk as is projected so that we can design and locate and site that plant or facility the best way we can. So these are tools that I just want to emphasize are important for planners and operators to use because they give us some flexibility. We can choose the intermediate curve for certain types of assets if we're willing to accept some risk in the planning and design. We also have to sometimes make trade-offs because if we plan to higher standards, our costs increase. So you can make some judgments and trade-offs along the way. This gives you tools, though, to work with. Okay, so what does sea level rise mean for our communities? It means that our floodplain is going to be expanding. That as the high tide rises with sea level rise, and you can imagine during storm events, storm surge is on top of that high tide, the water is moving landward and our floodplain may expand. And that means that there could be less viable land to build on or relocate infrastructure to. It could mean worsening impacts from storms, from both erosion or storm surge. Flooding obviously will be worsened by sea level rise, and we can anticipate more damage to infrastructure that is exposed to that flooding. Here's just a quick graphic showing that just in terms of tidal flooding, that's flooding based on high tides or spring tides up and down the coast. Over time, we've experienced an increase in the amount of flooding in low-lying spots. Some of you may recognize the term nuisance flooding. That's often used to describe these kind of floods. And I'm not going to spend too much time on these in the interest of time, but these are, in Delaware, we did an assessment, a vulnerability assessment of our infrastructure, looking at water supply, wastewater, transportation, and other systems. And we had, we show here I've taken an example of the number of public wells exposed to sea level rise and the number of irrigation wells. And we know that drinking water reliability in Delaware is highly dependent on surface water withdrawal, both in Newcastle County, which is in the northern part of our state. And the rest of the state utilizes groundwater for drinking water. Irrigation wells actually account for the largest use of groundwater in Delaware. And as sea level rises and the shorelines potentially recede landward, saltwater intrusion into our coastal aquifers will increase. And sea level rise will definitely exacerbate these problems. So that could mean salinity near drinking water intake pipes that affect the quality and reliability of drinking water, changes in functionality of our water wells. That could also prevent the expansion of water supply networks in the future. Future development could be constrained because of system capacity limits. Here's an example of some of the findings related to wastewater treatment for Delaware. By the way, I just want to caveat that these are based on 2009 sea level rise scenarios. which were just updated last year and only changed slightly. But in Delaware, as with many mid-Atlantic states, we have low-lying wastewater treatment facilities that could be subject to flooding. And certainly they could be these short-term, well, the impacts could be short-term if it's just tidal flooding, but in the long term, as sea level rises, the situation can become more chronic, and adaptation will likely be required to maintain full functionality. So when a facility is inundated, operators may be forced to bypass the treatment process. They may be forced to release the untreated waste into nearby rivers and streams, and that can impact water quality and recreational opportunities. We could also potentially see sewer line backups into houses. So there's definitely public health and public safety aspects to the impacts from sea level rise and wastewater treatment. I just sort of like this graphic because it tells us that we have to pay attention to not only existing conditions on the ground, but future conditions. And that's why looking at climate projections is so important in terms of resilience planning, because if you only look at current conditions or past history of flooding, it's like driving with your rear view mirror. You're looking backwards and you're not looking forward. So now I'm going to talk about resilience planning. And I'm going to kind of boil it down into a nutshell of 5 steps. These steps are really, you can look at various guides on resilience planning, also called adaptation planning or vulnerability planning, mitigation planning. But essentially, they all cover these 5 steps in some form and order. First is to inventory infrastructure and assets. What are you examining? What are their, what are characteristics about them that you need to understand? Number 2 is characterizing both the existing conditions and the future hazards. 3 is identifying and prioritizing vulnerabilities. So once you compare them to the hazards, you'll understand the exposure and risk that's involved, and then you'll develop ways of prioritizing those vulnerabilities. I will talk to that. And then we'll talk about, and then the next step is identifying mitigation and adaptation options that will help you address some of the vulnerabilities and promote your resiliency. And then 5 is determining the next steps and potentially the resource needs. And along the way, I can't emphasize enough that it's so important to collaborate and communicate. If we are a utility operator, even if we're kind of used to managing our system on our own, it's so important to engage with our stakeholders, to engage with our municipal officials, and to involve their input along the way. Plus, it's helpful for buy-in. The truth is that resilience planning is going to take a whole community scale effort. It's going to take a lot of resources, and we have to move everyone towards the need to acknowledge the importance of resilience planning. And the more that you engage others and that you get the infrastructure planning integrated into plans, whether they be comprehensive plans at the local level or hazard mitigation plans at the state level, the better that's integrated, the more success you'll have in the long run of gaining public support and hopefully some resources to do the adaptation work with. So the first step is inventorying infrastructure and assets. When you begin resilience planning, you need to understand, well, what are you looking at? Because vulnerability assessments and resilience planning can be scaled differently. You can look at one particular site or facility, or you could look at a whole community worth of assets and facilities. So it's important to ask yourself, what is important to the continuity of town operations? What's important to the social fabric of the community, to the quality of life? Maybe you're looking at vulnerable populations and how they're impacted. So it's important to know the scope of your effort. Once you select that scope or which infrastructure you're going to study, you're going to identify the location, the elevation of the infrastructure or facilities that you're looking at. So my examples are more infrastructure based. You're going to look at things like wells, pump stations, tanks, or generators. And you're going to assess the age and condition of them and look at interdependencies. And you have to know how far out you want to plan to. Are you planning out to 20 years or 30 years? Maybe 50 years. Sometimes with infrastructure, we need to plan a ways out because of the lifespan of that infrastructure. But I've worked in communities where these communities have a lot of retirees, and truthfully, and these communities, by the way, are fairly rural. They don't have a lot of capacity to undertake a lot of major change and mitigation. And so 20 to 30 years out was the right timing and planning time frame for us to embark on, because they can get their arms around it and it doesn't overwhelm their capacity. The next step is characterizing existing and future hazards. You need to start with past history, of course, which for flooding purposes and sea level rise, it helps to start with the FEMA floodplain maps. These are the regulatory floodplain maps that are used to guide insurance and assess risk at the local level. And they will tell you the elevation of the base flood based on a 100-year storm. 100-year storm is sort of a misnomer, because it really means that over a 30-year lifespan, that particular property in a 100-year zone might have a 26% chance in any given year of being flooded. So it's a 1% chance storm, really, but over a 30-year time span, it equates to a 26% chance per year of being flooded. It's also helpful to look at tide data, the facility's flood history, and then looking forward. You want to not be in the rearview mirror, you want to look forward. You want to consult with climate projections and inundation mapping tools that can help you assess the risks into the future, as well as visualize those risks. Visualization can be very important in communicating risks to others. I have a link here on this page to the FEMA Map Service Center, which is where you would go to access floodplain maps and other products. I'm not going to spend much time on this, because I've showed the scenarios in Delaware before, but essentially these projections of sea level rise, for example, these are crucial to knowing where you're going to plan to, selecting your planning time frame, and choosing what level of risk you want to plan to. This slide shows examples of some of the visualizations we use in Delaware. We have our own customized sea level rise inundation maps, but I put a link on this slide of a NOAA sea level rise viewer. That's a great tool for anyone in the nation to go to. It provides information, sort of like a bathtub model for inundation, and it helps you look at the landscape, imagining the kind of inundation that might be experienced under different sea level rise scenarios. So use that for planning and assessment. And then based on the mapping that you do and where the infrastructure that you're looking at falls within that mapping, you can identify the vulnerabilities and begin to prioritize them. It's important often to have criteria that you have to do the prioritization with. Criteria can include the importance of the facility or asset to the continuity of operations, or the importance of it to the health and well-being of a certain population in town. And then the process to identify adaptation and mitigation options commences, hopefully with a lot of stakeholder input. Stakeholders often can give you the best sense of what is likely to go over well, or what will address some of the needs in the community. And you'll get the buy-in the more that you involve them. Examples of adaptation and mitigation are things that accommodate the water, pumps, elevating utilities out of the way, elevating pole pump stations, and securing tanks so that they don't float away and become projectiles in a major flood. Or protecting the infrastructure from water. That's sort of creating barriers, whether it be through dikes or floodgates or flood walls around important distribution and piping systems. And it can include natural protection systems like our wetlands, which are amazing at absorbing excess flooding and inundation. And then there's the options of avoiding altogether by not building in the floodplain, by not expanding into the floodplain if you're in an existing facility, or retreating, which could mean relocating outfalls and pipelines, setting back a structure, moving it up to higher ground to avoid, to avoid your exposure and risk. And so I'm going to spend just a couple minutes talking about an example of resilience planning in action. And depending on time, I may not have enough time to go through the second example. So let's see how far along we get. This is the city of Seaford, Delaware. We did a vulnerability assessment for their wastewater treatment facility. It was built in 1961 and it's located on the Nanticoke River. It treats over 2 million gallons per day of wastewater from residential, commercial, and industrial sectors. And they're required to undergo an upgrade and expansion of their facility per NIPD's requirements in a few years. And so they wanted to complete a vulnerability assessment to inform the design of the upgrade. This is a great example of them being proactive and anticipatory and gathering information now to help with their resiliency planning so that when they design those upgrades, it can be designed with future flood risk involved in that design. So they began step one. They hired a contractor, and the contractor inventoried all of their facility structures and obtained the age and precise elevations of those assets. They determined which of those assets could not lose functionality during the event. Here's an example of some of the information that they gathered. By the way, so that's the Nanticoke River right along the bottom right edge of that property. And that's part of a tributary of the Chesapeake Bay. They agreed, upon a planning time frame of 30 years. I think that was because they knew that some of the upgrades they were going to need to do had a functionality of 20 years, but that the onset of that of the process to upgrade the facility was still a few years out, so they gave themselves a 30-year window. And they worked, so based on the 30-year window, and because of the importance of wastewater treatment to the continuity of town operations and to public safety, in terms of like if there were functionality deterioration of the facility during a flooding event that could impact public safety and health, they went with the higher scenario, which is the red line, because they had a low tolerance for risk. So that was what they went with, and basically you can see there around 2050, it was 0.5 meters of sea level rise that they were looking at. And that translates to 1.5 feet. Then they, step two, they reviewed FEMA floodplain maps, and the property was in part of the floodplain based on the 100-year flood. This example here shows the inundation that might be expected from that 100-year flood, also known as a 1% chance storm. And then they looked into the future at sea level rise using the Delaware sea level rise projections. and they combined in the mapping software like ArcGIS, they were able to show both the 100-year flood and the 1.5 feet of sea level rise based on the projections for sea level rise to show the amount of inundation that might occur based on the elevation of the different assets in the facility. This helped them identify right off the bat where the different assets, which assets might be more vulnerable than others. So they recorded the risks for each. They populated a table where they identified the different assets based on their elevation and whether there would be inundation expected and how much under these different scenarios. They included higher scenarios for sea level rise as well. And then they began to prioritize. They prioritized it based on degree of risk and the criticality of the system to operations. So they used a rank of 1 to 5, with 1 having the greatest importance for mitigation. And I just want to mention at the bottom that TOW is the top wall elevation, FF is the finished floor elevation. Finally, they documented the potential mitigation options, and examples are listed. One example is listed here. They identified some of the potential options that could be employed. For example, at the primary pumping station, they looked at flood-proofing doors. They identified potentially constructing a surrounding wall and so forth. And in their final report, they identified some future implementation steps that will help guide the design and planning process. So basically, they're helping to narrow in on which potential options to design for. That's an example of one facility undergoing a resilience plan. Other communities sometimes do comprehensive vulnerability assessments, which look at a totality of their facilities in their town. The city of Newcastle has 5,400 residents. But due to time constraints for our presentation today, I'm not going to be able to go through all of these slides, but I will just say that this community has a number of dikes that had been built in the 1600s. And that was designed to prevent inundation to farmland back then. So they were interested in understanding risks to those dikes from flooding, as well as other infrastructure in town. They inventoried their assets, including a lot of public works facilities. They identified existing hazards based on FEMA floodplain maps and future hazards based on climate projections. They selected what level of sea level rise they wanted to plan to and how far out. They actually used 2 years, 2050 and 2100, and they did mapping to help visualize those risks, showing what structures might be in the path of inundation under the 2 different scenarios, which are highlighted here in orange and yellow. They also presented it in other formats that you see here. And they created tables so that they can identify and capture all that inventory and all the vulnerable assets. And then they undertook a step to identify and prioritize those vulnerabilities, looking at sensitivity, looking at adaptive capacity. They also added criticalness, which is sort of a criteria they came up with that relates to the importance of that facility to public safety. And I think I have a bigger example here, but the bottom line is that they identified quite a number of facilities. The higher the score revealed the criticality or importance rather of that system. So it was the higher priority equal the higher score. The MSD office is a municipal supply building for their utility, and they had a number of pump stations and utilities that basically ended up falling into the middle of the prioritization. Based on that overall prioritization, they engaged with the public, took input to develop adaptation options to help them come up with next steps, which I've listed a few of them here. It includes some specific steps like elevating their dikes, but also additional surveys that were needed to get additional information on drainage systems so that they could really understand the capacity issues that they were working with. I know we're getting close on time, so I'm going to end off with some select resources for you. The top is the source of the climate projections I was describing today, but I wanted to just call out the second bullet. This is the U.S. Climate Resilience Toolkit. It has a number of great tools available to you to look up climate projections, to do sea level mapping, and to even obtain state-by-state summaries for climate. And with that, I think I'll close here and thank you for listening in today. And I'll leave you with this one last quote from one of the fathers of floodplain management. Floods are an act of God, but flood losses are largely an act of man. Thank you.
Thank you, Daniela. That was an excellent presentation. I'm going to maybe ask one or two questions. I know that we're a little bit over time, so if you have to jump off, that's okay, but I just wanted to make sure that the questions were addressed. So one of our audience members was asking, how far inland does coastal planning typically apply? How far inland should you be thinking about sea level?
I think that really varies for the area. I know that for the state of Delaware, our entire state is actually considered a coastal zone because no location is more than 12 miles from a tidal tributary.
And so that would be community specific, and you should really check with your state sort of planning authorities.
Yes.
Excellent. And so I really appreciated the example of the city of Seaford and the, what was the other? And so one of the questions that I had was the using the scorecard that they used, where they were able to do that scoring sheet for the entire community. I think that was the Newcastle example. Have you seen examples of that, but specific to critical infrastructure for water systems, or can you adapt that for a water system specifically?
For water systems, so I can't say I've done one specifically, except for that wastewater treatment facility that was the Seaford example. But here in the Newcastle example, you have a number of pump stations and a number of pump stations and office buildings listed. So for a water utility, you might look at the elevations of your drainage, intakes and your outfall pipes and your storage tanks and your your electrical transmission apparatus. You have to kind of imagine all the critical components that are necessary to the functioning of that infrastructure, break that out, and then the physical assets you need to look at the elevation of those assets, as well as their age and condition. I hope that's answering the question.
Yeah, no, that's great. And then the last question was about sort of the comprehensive nature of resilience planning. It involves so many different stakeholders from around the community, and oftentimes the driver is not necessarily the water systems themselves, but what can a water system do to either drive that conversation or make sure they're prepared once the rest of the community is ready to engage on resilience planning?
Oh, that's a great question. My primary recommendation is to partner. Communities will often have nonprofit groups, perhaps university groups, maybe there's a sea grant in your area, or a federal or state agency with staff that are available to help you with outreach. And I think partnering can help leverage the expertise and outreach capabilities of others. And oftentimes we have similar missions. Your utility may want to become more resilient, and we in the community want you to become more resilient too. And so that can bring us together, and we can leverage our respective resources to engage others and create more of an outreach plan.
Excellent. And I think that's the last question. Thank you so much, Danielle, for helping us think a little bit more about resilience, how to define risk, the difference between adaptation, mitigation, and then providing some really great community case studies whose lessons learned can be applied specifically to water systems. We appreciate your expertise, and thank you very much. And thank you to all who participated.
Thank you.